We are on chapter 6, section 4. And so this section, we're going to talk all about reactions that happen to monosaccharides. So remember, that's one ring when we were drawing all those different kinds of sugars. So we're going to talk about two reactions. We're going to talk about going from that Fischer structure into a ring formation. And then we're going to talk about oxidation reduction reactions. So when we drew the Fischer linear structures, that's not really how sugars actually behave in nature. And so we're going to see that the sugars, when they're pentoses and hexoses, so 5 and 6 carbon monosaccharides, they actually kind of bend backwards and form a ring. And so the interaction occurs because of the opposite charges on the functional groups. And so if you have opposite charges and they attract enough, you're going to make a new bond, and there are some other bonds that are going to be broken. So we need to see what bonds are broken and what bonds are formed. So remember your functional groups, right? There's a carbonyl that's present in aldehydes. So what I've drawn up here for you is an aldehyde. And so we have this carbonyl group right here, and it's present in the aldehyde. We also have a carbonyl group present here in a ketone. In both cases, this carbonyl group is very, very reactive. It's very polar, right? There's a big electronegativity difference between oxygen and carbon. So it's very polar, and that makes it very, very reactive. And so we end up getting a partial positive on our carbon and then a partial negative on the oxygen. And so that partial positive charge on our carbonyl is going to attract the electrons of a hydroxyl group that's partially negative. So over here we have, this is our hydroxyl, remember that's R with an OH. And so what you're going to have is an interaction between this oxygen and this carbon, or this oxygen and this carbon, okay? And so I'll show you how that works in a sugar in a second. But if this bond forms between the carbon and oxygen, then you're gonna form something that's called a hemiacetal bond, right? And so here's an example. We have an aldehyde. So an aldehyde is just this, except it's been rotated. So the oxygen is sticking out over here, the R group comes out the bottom, and the hydrogen comes out the top. So you just kind of took it and watch, I'll show you. And you rotate it, and you get exactly what's down here, even though it's kind of hard to see now that it's at an angle, but okay. So what happens is that this carbon's partially positive, this oxygen is partially negative, they're attracted to one another, and you can form a new bond between that carbon and that oxygen. And what happens then is that the bonds here will be made, right? And over here, this is a bond that will be broken, and this is a bond that will be broken, okay? And what's our new structure? Our new structure here, here's our carbon that was making all those bonds, right? Here's the oxygen. It was a double bond. It's no longer a double bond. Now it's a single bond. But in order for oxygen to be happy, it needs one more bond. So it will actually bond to a hydrogen in order to complete its octet. And then here's this new bond that we formed between the aldehyde carbon and the oxygen on the alcohol, okay? So here's our bonds formed right here. We have another bond formed right here. And then we broke a bond here, and we broke a bond here, okay? So we're gonna look at how this works. So monosaccharides usually exist in a ring. And it's because of that reaction of the carbonyl group with the hydroxyl. So let's kind of look at what this means, and I'm going to take it piece by piece. Okay, so we're going to kind of focus here on this part. So here's our Fischer structure, our Fischer projection, right? So here's our carbonyl group, right? And so I've kind of highlighted that oxygen in orange, so it's really easy to see. And so when you number your carbons, this carbon is going to be carbon number 1, and the carbon all the way at the bottom of your Fischer structure is carbon number 6. And so what's going to happen is this carbon is partially positive, this oxygen is partially negative. And so this carbon's actually going to kind of bend in order to come close to this oxygen, and they're going to be attracted to one another. So that's why I drew my green line, because my green line is going to be a new bond. And so when that happens, here's the molecule, it kind of bent over. Here's my oxygen from my hydroxyl group, right? And then here's my carbon from my carbonyl. And so we're going to make this bond between the hydroxyl oxygen and the carbonyl carbon. And we're going to lose a bond right here. This one, we're going to lose, oh, I'm sorry, this one. We're going to lose that one right there. And we're going to lose one of the bonds in the double bond in the carbonyl. And so instead of being carbon double bond oxygen, you end up being carbon single bond oxygen. Okay. So when you're drawing this structure, what you want to do is you want to remember that it's going to turn into a ring, and you got to think about what's going to be in that ring. So what's going to be in that ring, you start counting from the carbonyl carbon. We're going to have 1, 2, 3, 4, 5 carbons and 1 oxygen for a total of 6 atoms in the ring. So let's see if that worked. So we're going to start here. 1, because that's this carbon right here. 1, 2, 3, 4, 5 carbons and 1 oxygen. So that makes 6 atoms in my ring. Be very careful about that. You need to practice that, okay? All right, so now when you're drawing this, what I would do is I would start out with my ring, and I know over here is going to be my oxygen. I'm going to come down, right? Okay, now you have to fill in all the stuff around it, right? So if this oxygen, right, is, let's see if I can do this, is this oxygen right here, okay? That makes carbon 1 right here. This is carbon 1, all right? So what's gonna be attached to carbon 1? Well, you're gonna have this hydroxyl, right? And you're gonna have this oxygen here. So this carbon right here has 1 oxygen bound within the ring, and then it's gonna have another oxygen that's bound outside the ring. So what you do is you draw kind of a stick. And so that's telling you that this carbon right here has 2 things bound to it. One of them is an oxygen, and that oxygen is that orange oxygen, right? And then it also has a hydrogen. But that oxygen is not happy all by itself, just an oxygen, because it only has a single bond, so you're going to give that a hydrogen, okay? And then what you do is you go around and you're going to put things around the ring depending on how they are in the Fischer structure. So there's a little thing you should remember, that if it's on the right side of the Fischer structure, it's going to go in what's called the bottom of the ring. So you got to kind of think about the ring, right? We're looking at the ring kind of like this, right? But now take that ring that we just made and lay it down on a paper, right? And so what you're going to see when you lay it down on the paper is anything that I drew going up, like this hydrogen right here, this hydrogen is actually going to be coming up, and this hydroxyl group down below is going to be going downward. So if in our 2-dimensional drawing it's pointed up, that means it's actually going up in 3 dimensions and going down in 3 dimensions, okay? So our little trick is, if in the Fischer structure it's on the right side, it's going to go on the bottom of the ring. If in the Fischer structure it's on the left side, it's going to go on the top of the ring. So all of this stuff is going to go in the top of the ring, okay? So now, I know where my carbon 1 is. The oxygen that's blue is on carbon 5, is attached to carbon 5. So I can't go this way. I can't go 1, 2, because that's an oxygen. I want to count my carbons. So I got to go 1, 2, 3, 4, 5. So I have 5 carbons in my ring and 1 oxygen. So what's attached to 1 through 5? Well, 2, right? If I look at carbon 2, I have a hydrogen and a hydroxyl. which one is going to be pointing up? That's my hydrogen. So I'm going to go up. I'm going to put a hydrogen there. And then I'm going to put hydroxyl there. Do the same thing on the next one. The next one, I have an OH that needs to go on the top. OH. So that means my hydrogen goes on the bottom. Okay. Now number 4, carbon number 4, I have a hydrogen on top and hydroxyl on the bottom. And then number 5, now be careful with number 5 because there's a bunch of stuff with number 5. Attached to number 5, we have our blue oxygen. Well, we already drew that. Attached to number 5 is our blue oxygen. We did that. So what's left? I have a hydrogen. Let me erase this. What's left is I have a hydrogen and then this extra group right there. So what goes where? Well, here's the trick. This thing at the bottom, this carbon number 6, that's always going to go on the top. Always, always, always going to go on the top. So draw your little stick, CH2, OH, and you put our hydrogen there, okay? It is going to take practice to do this. You're gonna have to practice. So let's check our structure. Does our structure look like what the book has? And yes, it does. Okay, now, that's one way that this could happen. The other way that this could happen is if, and I'll show you, if this portion right here gets flip-flopped. If that portion gets flip-flopped, at the bottom I would have an oxygen, at the top I would have a hydroxyl. So that would be my flip-flop. And so what I see is here's where that is flip-flopped. I have hydrogen on the bottom and I have hydroxyl on the top. And so when the ring forms, either of these configurations can happen. And so we call the top configuration alpha, and we call the bottom configuration beta. So these are 2 possible anomers of the same molecule of glucose. So we call the top one alpha D glucose and the bottom one beta D glucose. And so how do you remember what's what? Well, we look at how the hydroxyl is arranged in relation to the carbon group that comes off of carbon 5. So if I look at that, let me change color here. If I look at my hydroxyl in relation, here's my hydroxyl, in relation to my group that's coming off of carbon 5. If they are on opposite sides of the ring, remember what I said about going up and going down? If it's going up, it's at the top of the ring. It's on the top surface of the ring. If it's pointed down, it's on the bottom surface of the ring. So if they're on opposite surfaces of the ring, then that's telling me, remember opposite, what did opposite mean? Opposite is trans, but we don't call it trans in this case because it's not a double bond. We actually call it alpha and beta. So trans means alpha. And sometimes you'll see alpha abbreviated as this little, let's see if I move my picture, as this little, it's like an A, and I'm not the best person at drawing it. It's like an A, but it's got a little tail, but that just means alpha. Okay, so just remember when you're drawing this structure that one of your carbons, carbon 6, is not going to get incorporated into the ring. It's going to remain on the outside of the ring. And the relation of this carbon that sits outside of the ring to your hydroxyl group is going to tell you if it's alpha or beta. So let's look at the next one. The next one, here's our carbon that's sitting outside. We're going to compare it to our hydroxyl. Well, look at this. They're both up. Well, if they're both up, they're cis. And the way that we say cis in a ringed sugar is we say it is the beta configuration. Or here's a little symbol for beta, right? When you're looking at these structures, and I have all the notes for this stuff, but I wanted to show you pictures before you take notes. is you need to be able to find in these structures what's called the anomeric carbon. So it's the carbon that's bound to 2 oxygens, because that one's really, really important when we get to some other structures. And so if you look in this figure, there's only 1 carbon that is bound to 2 oxygens. And that 1 carbon is right here, because it's bound to 1 oxygen on the ring, and then it's bound to 1 oxygen outside of the ring. And it's going to be very important to be able to find that carbon when we're making some other structures. So kind of keep that in mind. Okay. So let's kind of take our notes on all the things we did. That was kind of a lot. So to summarize, right, we can make 2 structures when we go from a straight chain into a ring formation. And why does that happen? Because the oxygen on the hydroxyl group of carbon 5, so the oxygen on carbon 5, the oxygen on carbon 5 will form a bond, right, with the carbonyl. And either that bond will go on the top of the ring or the bottom of the ring. And we call that alpha beta anomers. So in any monosaccharide, the carbonyl carbon that reacts to make that hemiacetal bond is going to be the anomeric carbon, right? They're anomers, so anomeric carbon. And remember that when you're looking to identify where's the anomeric carbon, it's the only one that's bonded to 2 oxygen atoms. So if you're analyzing a structure, that's how you find it. And so we said there are 2 anomers, are the alpha and the beta anomers, and they're only different by the positioning of that hydroxyl group on the anomeric carbon. And how do we know what we're comparing it to? We're comparing it to the position of the carbon that is on the outside of the ring, right? So, right, we had our basic structure sort of like this. So we had our hydroxyl either at position A or position B, and this was our CH2OH, right? So depending on how that hydroxyl is that hydroxyl in position A or position B, is going to tell you if it is an alpha or a beta anomer. So if it's an alpha anomer, oh, you know what? And I really should have done it the other way around, right? A and B, right? Because if it's in position A, based on that drawing, right, the OH is trans to our carbon 6. They're on opposite sides of the ring. So if they're on opposite sides of the ring, trans gives you the alpha anomer. If they're on the same, so like B and our carbon 6, they're on the same side, then they're the beta anomer because they're cis. Okay. All right, so whenever you're trying to do this, here's a kind of like your step-by-step what to do, right? You're gonna start with, and I don't know why your book didn't like give you the structure of the Fisher structure, which you're working off of. So if you want to pause the video and draw that structure, that would probably be a really good thing to do, so you can see what we really started out with. So we start with our Fisher structure. Your carbon 1 is the one that has the carbonyl attached to it. It is part of the carbonyl. And then number going down, right? And so when you do this, you're going to have to make a ring. Oxygen is going to be part of the top of the ring. And on the opposite side, you're going to put C6 attached to C5. So here's our C6 right here, and it's attached to carbon number 5. And that makes sense because C6 is attached to carbon number 5 right there, okay? All right, so then when you're doing it, you have to read the problem. Is it telling you to make an alpha? Is it telling you to make beta? Depending on which one it is, depends on where you're gonna place the hydroxyl group that was on that carbon 5, right? Well, no, that was on the carbonyl, excuse me. That was on the carbonyl. And so if you're told it's alpha, you put them in a trans orientation. If they tell you it's beta, you put it in a cis configuration. So if you look here at this one, right, our carbon 6 is up here, our hydroxyl's up here, and so what must this be? This must be the beta anomer because they are cis. And then you just fill in the remaining atoms. Whoa, and I'm going to show you, I'm going to walk you through one. But remember that those that are on the left are placed on the top. Those that are on the right are placed on the bottom. So let's do a couple of these. It's important that you find that anomeric carbon, right, when you're doing this, because that's going to tell you whether this is alpha or beta. So make sure that you know which carbon you're looking at. So let's do our first one. If I want to first find my anomeric carbon, I want to know, is this an alpha anomer or a beta anomer? This is my anomeric carbon right there. My anomeric carbon is bound to 2 oxygens. There's one and there's the other. So this is the carbon I'm looking at, because all the other carbons have hydroxyl groups attached to them as well. So how do you know you're looking at the right carbon? Because you know this is the only carbon that's attached to 2 oxygens. So if I compare my two, I have my hydroxyl group down below, I have carbon 6 up above. So if they are opposite, that means they are trans, and trans is telling us in this case that it is going to be alpha, right? So you just got to remember trans and alpha. All right, now find your anomeric carbon. Here's my anomeric carbon bound to 1, 2 oxygens. I want to know if we are alpha or beta. I'm going to look at carbon 6. It's on the top. I'm going to look at my hydroxyl. It's on the top. So this is the cis configuration, and the cis configuration is our beta configuration. Okay, and you could have just abbreviated that. The B, it's like the B with the little stick. Alpha, you can do just kind of an alpha. Either way. All right, now look for your anomeric carbon. My anomeric carbon is the only one that's bound to 2 oxygens. Notice that this ring's a little different. This ring only has 4 carbons instead of the other rings that had 5. So here it's bound to 1 oxygen. Here it's bound to the other oxygen. So I'm going to look. Here's my carbon 6. Here's my hydroxyl. They're both above. So they are cis, and this is beta. Okay. So those aren't too bad. All right, now draw a ring from a linear structure. All right, the instructions tell me draw the alpha anomer of D-mannose in pyranose ring form. All right, so what does alpha mean? Alpha means trans, so kind of remember that when we're writing it. And then I wrote our little note on the side at the top up here, right? If it's on the right side, it goes on the bottom. If it's on the left side, it goes on the top. So let's draw kind of a line of what's going to happen. We know that our OH on our 5th carbon, on the carbon down here, is going to come up and try and bond with this carbon right there. So how many carbons are we going to have in the ring? In the ring, we'll have 1, 2, 3, 4, 5 in the ring. 6 is going to be pointing up, right? So we'll have 5 carbons in the ring, plus what else is going to go in the ring? If I start here at this carbon, I'm going to work my way down through the other carbons. Oh, and then I'm going to hit an oxygen. Whoa. Then I'm going to hit an oxygen, and then I'm going to have to go up to meet the carbon again to make a ring. So I should end up with 5 carbons and 1 oxygen in my ring. So if I do that, this is what I end up with, right? There's my 1 oxygen, and then I have 1, 2, 3, 4, 5 carbons, but then I have to worry about my 6th carbon. I know my 6th carbon is always going to come up here and be CH2OH. All right, now we're going to draw the alpha or trans anomer. So we go find carbon 1, right? Ooh, kind of move that in. It's carbon 1. So we want to do a trans. Trans, we're going to be on opposite sides. So wherever my carbon is, I don't want to put it up at the top because the carbon 6 is at the top. I want to put it down at the bottom. So that's my OH. And then I also have a hydrogen attached. Now I'm going to go to carbon 2. Remember, everything that's over here, right? Everything on the left side is going to go to the top. So my carbon 2, I have an OH and I have an H. Carbon 3, OH is on the top, H. Carbon 4, I have a hydrogen on top and then a hydroxyl. Now, when you get to carbon 5, you have already put this in because that's this, right? You've already put in the bond to the oxygen. That's this right here. So what else do you need to put? You've put the bond to the carbon above. That's that one. What else do you need to put in? You need to worry about, guess what? This hydrogen right there. So where does that hydrogen go? That hydrogen goes right there. So if I remove my numbers, it might make it a little bit easier for y'all to see and to understand what's going on, right? So you can see the structure a little bit more clearly. So you need to be able to do that. All right, so D-fructose is a ketone, right? And a ketone is different than an aldehyde. Remember, ketone, you need two things, lock and a key. So, right, we have our carbonyl, and then we're gonna have something bonded up top, an R group up top and an R group at the bottom. That's our ketone. And so what you're gonna look for is the OH on carbon 5 actually curling around to react with that carbonyl. So if you zoom in, here's just an example. If you wanna draw this, I'll show you a diagram in a minute, but it's the same basic process, right? Your oxygen is gonna come up and it's gonna make a bond with that carbon from the carbonyl. So it's the same process, but look what's different. What's different is we're gonna have fewer carbons in that ring. So it's gonna be a smaller ring. All right, so our carbon 5, and that's what we said, this is carbon 5, can curl around and react with the carbonyl positioned at carbon 2. So that's our ring structure. So you have 4 carbons, you have 1 oxygen, and so you get a 5, they call it a 5-membered ring. That means it has carbon and some other elements, and in this case, it's oxygen. Okay, I did want to show you this, okay. So you can just kind of skip ahead, right? Here's our Fischer structure, and so what's gonna happen is, this is our anomeric carbon, because eventually it's gonna be bound to 2 oxygens. We're gonna make that bond right there, and what's gonna happen, we're gonna turn into a ring, right? So our oxygen here is this oxygen here. And this carbon right here is this carbon right here, okay? So once you form that ring, what you're gonna do is you're gonna say it's got 1 less member to the ring. So remember how our general structure for our ring before was like this? This is a 6-membered ring. Well, a 5-membered ring just kind of looks like the house, sort of, right? And so in this one, we had an oxygen here. In this case, we're gonna put our oxygen like at the roof of the house, on the tip of the roof of the house. Okay, so remember your carbon 6 is still gonna stick out on top, but now you also have carbon 1 that's going to stick out. Now, you don't know where carbon 1 is gonna go, because that carbon 1 is going to be bound to the same oxygen, it's bound to the same carbon that has that hydroxyl group on it. And so this is determining your anomer. So you don't know if that hydroxyl is going to be up high or if it's going to be down low. If it's up high with the 6, like it is down here, it is cis, and we know cis is beta. And if it is trans, we know that trans is alpha, okay? So just kind of be careful with that. But it's the same rule. If it's on the left, it goes on top when you're drawing these. Okay, and so this is what we just said, that alpha and beta anomers are determined by the position of the hydroxyl group, not carbons. It's determined by the hydroxyl group relative to carbon 6. Okay. All right. So the next kind of reaction we're going to talk about are oxidation reduction reactions. So remember your aldehyde. There are sugars with an aldehyde. We call those aldoses, right? Just telling us it's a sugar. Those can undergo oxidation reduction reactions. And remember, an aldehyde, all alone aldehyde, only has one R group. Then it has our carbonyl right here, and then you're bonded to a hydrogen. Okay, so this is why it was super important for you to learn those functional groups last chapter. You're going to need them. Okay, or 2 chapters ago. So when we undergo oxidation reduction, when we talk about organic compounds, we're going to talk about gaining or losing oxygens or hydrogens, right? So if you oxidize, you're going to add oxygen. So oxidize, add oxygen, O and O. If you reduce, you're going to add hydrogen. So if you always say it in terms of add, then you're always going to get it right, because oxidation is add oxygen. Okay? So if we have an aldehyde and when it undergoes oxidation, so we're going in this direction, what you're going to form is a carboxylic acid. So you remember your carboxylic acid is that carbonyl group right here bound to an alcohol, and we call that a carboxylic acid. If on the other hand, let me erase some of this. If on the other hand, it undergoes reduction. If it undergoes reduction means we're going to add a hydrogen. So if I just stick another hydrogen on there, I'm going to have to get rid of this bond. And then I end up with carbon surrounded by hydrogens and then an OH group, and that is an alcohol. Okay. So these functional groups exist in sugars, in monosaccharides. And so you have to kind of think about them in terms of monosaccharides and not just functional groups. So instead of it being an aldehyde, if it's with a sugar, it's an aldose. If the aldose undergoes oxidation, it's going to produce, instead of a carboxylic acid, we're going to say it's a sugar acid. If that aldose undergoes a redox reaction or a reduction, you're going to turn into a sugar alcohol. Okay, so just put the sugar in there. So you can use a test, what's called Benedict's test, in order to determine if you have an aldose inside of your solution. And the way that this works is you add copper 2 ions to solution. And if you've ever, I don't know if you've ever done this in a high school chemistry, but if you put copper 2 ions just in solution, they actually it turns blue. And so your solution would be like this, this really, really pretty light blue. And so if you have an aldose, right, in there, you've got your aldose, you put your Benedict's test solution in there, it's got the copper 2 ions, it's going to be blue. Now, if you add a product in there that has the aldose, what's going to happen is it's going to undergo oxidation. And when it undergoes oxidation, we're going to add an oxygen. So here I went from a carbonyl, here's my carbonyl, bound to a hydrogen. But in this case, I'm going to add an oxygen. So here's my new oxygen, right? So what did I make? I made a sugar acid through oxidation. But what did we say about all oxidation, reduction, oxidation reactions? That if you have something that's undergoing oxidation, something else has to undergo reduction. And so that's what happens with your copper 2 ions. They start out as a +2, and then they undergo a reduction, and they turn into a Cu+. And that Cu plus is actually in a compound, and that compound is called copper 1 oxide. And so copper 1 oxide is not soluble, and it will actually precipitate out into these like red little, it's like brick colored granules, and the solution turns kind of orange. And so if you have aldose present, your solution will go from being this pretty blue to kind of this orange with kind of like clumpy things at the bottom, right? And this is actually super, super important because you can use this to check diabetics. So down here at the bottom, you can use this to check diabetics, because if diabetics have high blood sugar levels, usually they have high sugar levels in their urine as well. And so you can do a really quick Benedict's test on urine and determine how, just kind of a relative number. It doesn't give you an absolute number, but you can tell if it's high or low in a diabetic. So it's pretty nifty little trick. Okay, so those aldoses that we talked about that became oxidized, they became oxidized, which facilitated the reduction of the copper ion. So anything that is actually oxidized becomes a reducing agent, because it was the activity of this molecule that forced the reduction of our copper 2 to copper 1. So we call them reducing agents. And in this case, it's a sugar, so we call it a reducing sugar. Fructose and other ketoses are also reducing sugars, and they don't form exactly the same reaction, right? They don't have an aldehyde group, but they can rearrange into an aldose in the presence of an oxidizing agent. So it's just something that all monosaccharides can do. They're all reducing sugars, and you can check them with the Benedict's test. So this is what your solutions look like. If it is negative for the sugar, you've put your sample in, your solution will stay this pretty blue. And if it becomes positive, it gets cloudy, gets clumpy, and kind of orangish. They call it brick red, but you know. All right, so remember how we said that our aldoses and our ketoses can be reduced to an alcohol, right? Well, what's really interesting about these molecules is that they still taste sweet, but we don't process them in the same way. So because we don't process them down and get calories out of them, get energy out of them, these are our basically artificial sweeteners. So sorbitol, xylitol, erythritol, all of those are the components that are in like those pretend sugars, right? And so we have an enzyme inside of our bodies called aldose reductase, and it reduces our excessive, if you get really high blood glucose levels, it reduces them to sugar alcohols in our blood. And if you have a person who that happens to very often, and that would be somebody, for example, who has diabetes, it can actually contribute to high levels of cataracts. So this is why they check diabetics for cataracts so often. All right, so our example, draw the product when D-galactose undergoes oxidation at carbon 1. All right, so remember in this example, if it's undergoing oxidation at carbon 1, what's happening? What's happening is our aldehyde group, right? Here's our aldehyde group, is going to get converted into a carboxylic acid. It's going to get converted into a carboxylic acid. So how's that going to work? Well, this one's actually like super easy to draw because the rest of the molecule doesn't change. So I can just kind of copy it. Oop, I could try, and I could paste it. Okay, so now I'm going to make my product. So what's going to change? Well, if I'm converting to a carboxylic acid, remember the general format for a carboxylic acid is this, right? And you have that R group. So all of this is the R group. So all you have to change is this stuff up here. Well, my double bond, my oxygen to my double bond is going to stay. That's fine. So what's going to happen? all that's going to happen is that this hydrogen right here, we can scratch that out, is going to get converted to a hydroxyl group. And that's it. That's all. Super easy. Don't you love those? All right, let's go and do some problems. All right, so we got our problems here. Starting with 6.23, identify the following carbohydrates as the alpha or beta anomer. So make yourself a note, right? What does this mean? This means alpha means trans, beta means cis. And trans and cis for what? What are you comparing? You're going to compare the hydroxyl group on the anomeric carbon, right? This is the carbon bonded to two oxygens. And you're going to compare that to the last carbon in the ring. And this is the one that's on top, the one on top. So it would be this one and this one. These are the two things we're looking at, right? So are they both above, or is one above and the other below? They're both above. So if they're both above, they are cis, and cis means beta, okay? Okay, let's do the next one. Here we have our last carbon on the ring. Now be careful, be very careful. You have two hydroxyls. How do you know which one it is? It's not the one with CH2. It's not that one that you're worried about. You're worried about this one. It's the hydroxyl all by itself. So this one is, again, cis. So that makes it beta. Be careful with that. Okay. 6.25. Draw, a little bit tougher, the alpha and beta anomer of D-talose in a pyranose ring form. So what do we have to remember? Remember your alpha, right, is going to be trans. Our beta is going to be cis. And remember, we're going to just try and write ourselves some notes, right? That whatever is on the left becomes what's on the top, right? Okay, and where's my new bond going to form? The carbon in the carbonyl, and then the oxygen in that last hydroxyl group on that last chiral carbon. Okay, so how many carbons do I have? 1, 2, 3, 4, 5. The sixth carbon, this is going to be on the top. This is going to be on the top, okay? So I have 5 carbons in the ring, plus I have my oxygen, because you'll have a bond from carbon 1, there's carbon 1, to carbon 2 to carbon 3, 3 to 4, 4 to 5, then carbon 5 to oxygen, and then oxygen to carbon 6. Okay, so we should have a 6-membered ring. If we have a 6-membered ring, but oxygen is one of the atoms, that's like a tiny oxygen. Come on, big oxygen. Okay, so remember our carbon 6 is going to stick up on the top, so that's CH2OH. All right, now we know that we're going to have our carbon right here, and we have to decide where our OH is going to go and where our hydrogen is going to go. So let's make this one alpha, and we know alpha means trans, so I'm going to put my hydroxyl group on the bottom, my hydrogen on the top. So now I need to go and look at carbon 2. This is carbon 1, carbon 2. What's on the left goes on the top. So let me erase my numbers because we don't need those. So what do we say on top? OH, so what goes on the bottom? Hydrogen. Go to carbon 3. Carbon 3, OH should be on the top, H should be on the bottom. Carbon 4, okay, carbon 4, OH on the top, and then H on the bottom. Now, carbon 5, be careful. Carbon 5, we've already drawn this, so we don't have to worry about that. We've already put in our oxygen, right? That's this oxygen right here, so we don't have to worry about that. The only thing left that's going to go on this stick is this hydrogen right here, and that's going to go on the bottom. Okay, so that's our alpha. Let's do our beta. So we're going to draw the same ring. Okay. And we're going to do everything exactly the same except for our anomeric carbon. CH2OH, hydrogen, OH, H, OH, H, OH, H. Now, if it's beta, beta is telling me cis, so they have to be on the same side, and then hydrogen, okay? All right. Oh yeah, this one I want to do both 6.27 and 6.28. When an aldehyde undergoes oxidation, the functional group blank results. I want you to kind of draw this, right? What's an aldehyde? An aldehyde is a carbon with a carbonyl. Aldehyde's alone, so it only has one R group. The other one's a hydrogen. What's going to happen? You have two different reactions that can happen. You can have an oxidation reaction, or you can have a reduction reaction. In an oxidation reaction, you're going to add oxygen. In a reduction reaction, you're going to add hydrogen. So what's that going to look like in my reduction? Well, how can I add another oxygen to my carbon? I have one that's double bonded, and I have my R group, so I can't change my number of bonds. So I put an oxygen and then attach the hydrogen to that oxygen. So I get, this is a carboxylic acid. This one, I'm sorry, to start with was an aldehyde. And then what are we going to make in our reduction? Remember, you still have your carbon, you still have your R group, you still have your hydrogen. Now you're going to add another hydrogen to it. So I'm going to add my hydrogen at the bottom. Well, that's 4 bonds. I can't have a double bond anymore. So I'm going to have an oxygen and a hydrogen. What did I make? I made an alcohol. Okay. So look at our question, 6.27. When an aldehyde undergoes oxidation, the functional group blank results. When we undergo oxidation, we are looking at this side of the reaction, right? Oxidation. So what forms? What forms is carboxylic acid, okay? Now, when an aldehyde undergoes reduction, here's my reduction. What functional group occurs? Well, that's an alcohol, okay? So you need to be able to draw that stuff. All right, we have a sugar alcohol, ribitol, and it's a component of vitamin riboflavin and the energy transfer molecule FAD. So ribitol is formed when the monosaccharide ribose undergoes reduction at carbon 1. Tell me what's going to happen if we have reduction at carbon 1. Reduction means we're going to add hydrogen. Draw the structure of ribitol. All right, so I'm going to cheat a little bit, and I'm going to copy my molecule. Okay, there's my molecule. So what's going to be different? What's going to be different? Well, if I want to add hydrogen, right, that's my my reduction. I'm going to add H2. Where's that hydrogen going to go? That hydrogen is going to go to this carbonyl carbon. So where's it going to add? It's going to add here. You're going to have one here. So now carbon, has too many bonds attached to it, right? It can only have 4. So what I'm going to have to do is I'm going to have to go in and erase that double bond. Can we just do the double bond? There we go. Okay, and now I'm going to make a single bond. Now oxygen's not happy, oxygen. So we need to give it an H, right? Because we're making an alcohol. So that's great. I do want to tell you that another way that you could write this, and your book shows it this way sometimes. I don't care for it so much, but you're going to see it. So I want you to know what it means. Sometimes what they'll do is they will write this group right here in the condensed form. So you have a carbon do this. You have a carbon, right? That carbon has 2 hydrogens attached, and it also has an alcohol attached. And so what they'll do is, instead of having this stuff at the top, they will just write CH2OH. You know, you could see it either way. So, or, either one's acceptable. All right. 30 we're doing in class. Here we go, 31. Pentoses exist in a ring form, but they most commonly occur in fructose rings. D-ribose exists in this ring form in the nucleic acid RNA. Using the structure of D-ribose, draw our furanose form of beta D-ribose. Beta, what do you think of when you see beta? Beta is cis, right? Okay, so what we're gonna do is we're gonna take our molecule. Now see how your book does this? I hate that your book does this, I really, really do. Let's redraw our molecule. Let's redraw, see this CHO? Doesn't tell you structure. You need to be able to see structure. Okay, so what that really means is you have a carbon bound to a hydrogen, double bound to an oxygen, okay? So then let's draw in the rest of the molecule. And this will not be their perfect picture, but that's okay. I think it'll make a little bit more sense. Okay, then you have CH2OH. Okay, now we want to make it into a ring. How are we going to make it into a ring? What is going to happen? Our oxygen on the farthest chiral carbon will make a bond with the carbon from our carbonyl, right? So how many different things are we going to have on our ring? 1, 2, 3, 4. That's 4 carbons, 5 carbons, but this oxygen is going to be on the ring. So we're going to have 1 carbon, 2, 3 carbons, 4 carbons. Then we're going to have 5 is going to be our oxygen, and then we're going to come back to carbon. Okay. So if we want a 5 ring, remember it kind of looks like that house. Kind of comes in a little bit, and then a flat floor. Okay. So now I want the beta form, the beta cis form. So when I see my oxygen, I want to go over 1, and I want to put my group down here at the bottom, right? So I'm going to put a little stick on that one, and I'm going to call this CH2OH, right? Because this is actually carbon 5. No, that's actually carbon 4. That's actually carbon 4. Come on. Carbon 4, okay? Because here's our oxygen, and then we count this way, 1, 2, 3, 4, and then that would be carbon 5. So now we want to make our anomeric carbon. So we know this is our anomeric carbon, so we're going to put our hydroxyl and our hydrogen. But now our question is, which one? If it's beta and cis, I want to put my hydroxyl on the top, hydrogen on the bottom. Then anything that's on the left goes on top. So it's all going to be hydrogens. Let me kind of erase these numbers. It's all going to be hydrogens on the inside. Right? Oh, and don't forget this hydrogen right there. It's going to go right there. Okay. All right. And I think that's, yes, that's it. Y'all have a great rest of your day.